Hey guys, we're back with the notes for 7.4. I apologize, this is going to be a lengthy video. We got 3 pages of notes to get through, but I will try my best to get you as much description as possible without using as much time as possible. Okay, so we are working on properties of rational exponents. Basically, we're going to be going back and forth between fractional exponents and radicals and using them to simplify an expression without a calculator. Okay, so one of the things that I'm going to have you write down on the next page is some of the powers that I would suggest you memorize, either with note cards or just by looking at them over and over and over. That way, when you see them, you don't stress, you recognize those numbers. Okay? All right, let's go ahead and look down here. The little numbers with the circles around them is me telling you which property above that we're using. So when I put a 1 with a circle, that means we're using the first property. 2 with a circle, second property. Okay, so here's what these are going to look like. First property is that we are going to add the exponents whenever we are multiplying with the same base. Okay, so on this problem, in order to add exponents, I do need to have the same common denominator. So 1/2 is the same as 2/4. So if I add 1/4 and 2/4, we get 3/4. Okay, now I don't need to simplify that any farther. The point that I want you guys to understand is if you start with fractional exponents, you can end with fractional exponents. So I'm not going to be able to take a 4th root of 7, and I don't have to do 7 to the 3rd power. Okay, all right, let's look at the next one. Second property tells me that if I have an exponent on the outside and the inside, I'm doing a power of a power. These guys are going to multiply. So if I do 5/2 times 2, these 2's are going to cancel out, and I end up with 3 to the 5th. Now, that I do expect you to simplify. So 3 to the 5th power is one that I will expect you to memorize. I'm going to put a star next to it. That should be 243. Okay, so that's our final answer. If I can simplify it, I always should. Problem number 3, whenever you have a multiplication inside, and that might look something like 5x, or it might look like 16 times 9, you are going to distribute the outside exponent to both of the exponents inside. So both of them have little imaginary 1s right here. The only time this does not work is if you had a plus or a minus in the middle. As long as it's all one multiplication term, you are still good to distribute, okay? So I'm going to do 16, multiply my exponents, 1 times 1/2. Second one, 9 to the 1/2 power. Now, we know that 1/2 is the same as a square root, so I'm saying the square root of 16 times the square root of 9. Square root of 16 is 4. Square root of 9 is 3, which means my final answer is 12. I guess I could box these for you so you know when we're done. There you go. All right, last one on this row, number 4. Remember that when you have a negative exponent, you are moving it to the lower level, okay? So right now, this is like 36/1. I'm going to drop the level, so 1/36 to the 1/2. We know that 1/2 is the same as a square root, so that's 1/the square root of 36. And square root of 36 is 6. So we end up with 1/6 as our final answer. Do remember that technically when you square root something, you would have a plus or minus, but it only is required if you're solving. Okay? All right, let's look on problem 5. Problem number 5, whenever we have a power on top and bottom, but the bases are the same, we are going to subtract these exponents. So we're saying they have common denominator. 5/2 minus 1/2 should give me 4/2, which 4/2 is 2 whole. Oops. And then we can simplify. 4 squared would give us 16. That's my final answer. Okay. All right. Problem F. We are using the same 2 properties that we've already looked at as far as distributing the exponent and also a negative exponent. Okay. So first thing I'm going to do is distribute to both of these. Remember, they have imaginary 1s. So that is saying 27 to the negative 1/3 and 64 to the negative 1/3. Remember that negatives need to switch their location. Let me move that up, sorry. So my 64 is going to change to the top, numerator. 27 is going to go to the bottom. They both turn positive when they get there. And now when I have to the 1/3, that's the same as a cube root. So I'm going to take the cube root of 64 over the cube root of 27. Both of those are perfect cubes. So I know that the cube root of 64 is 4. That would be 4 to the 3rd power. And I know the cube root of 27 is 3, or 3 to the 3rd power. 4/3 is my final answer. Okay? All right. We have one more on this page. On G, we are actually going to undo the 6th property. Okay? So if I notice that these both have the same exponent, just like they were multiplied in, I can pull them out. Okay? So we're going to rewrite this. And again, it's multiplication. We're going to rewrite this by taking it out and doing 42 over 6. 2 times the 1/3 is 2/3. Okay? Except now by doing that, I can simplify the 42 over 6. So I can say 7 to the 2/3. And I don't need to do anything else. I can't take the cube root of 7, and I don't need to square it because I still wouldn't be able to cube root it. So that would be my final step, and I actually don't really need the parentheses unless it was negative. Okay? All right. That is all of our work on this page. I'm going to zoom out for just a second. If you would copy what you see, and then I do want you to understand right here, if you start with rational exponents, you should end in rational exponents. If you start with radicals, you should end with radicals, okay? That's the expectation for the problem. You can move back and forth between them if you need to, but you should never start with a fractional exponent and end with a radical answer, okay? Keep it in the same form. Let's go ahead and go to the next problem, or next page, sorry. All right, I am going to have you pause the screen and copy everything you see at the top. So that's going to be 1, 2, 3 things. Plus play when you're ready. Great. Okay, so here's some of the perfect cubes, that's 3rd power, and perfect 4th power numbers that I expect you to know. Okay, I expect you to know cubes up to 1,000. I expect you to know 4th powers up to 625, which is 5. 5th powers, I would probably only expect you to know 2, 3, and 4. And I didn't write those on here, but we did use 3 on the last page. Okay. All right, so here's what we're talking about with properties of radicals. Properties of radicals, just like when we simplified square roots, we are looking for, can I break it with a factor tree or without into numbers that would have cubes? So we looked for perfect squares before. Now we're looking for perfect cubes. So if I break this into 5 and 27, I know 27 is 3 and 3 and 3. Okay? If it helps you to write it out long ways, that's fine. But if I can break them apart separately and I can pull one of them to the outside, then I would do that. And anything else stays inside. Make sure that your little index here stay the same. Okay? Same thing on this side. If I needed to break up the radicals and apply it to the top and bottom, I could do that. If I need to make them the same and put them back together to simplify what's underneath, I can do that too. 250 is not a perfect cube and neither is 2. But if I put them together, I can cube root 125. Okay. All right, so let's go ahead and go down here. These are the rules for simplifying radicals. So this page mostly focuses on problems or options 1 and 2. We will talk about 3 and 4 on the next page. Okay? So on problem A through H, other than number F, we are focusing on trying to get n factors to be removed from the radical. So what I mean by that is this guy. Trying to find anything that would be a cube root or a square root or a 4th root that we can take out of that problem. Okay, so let's start with 200. I'm having a square root, so I'm saying, are there any perfect squares inside of 200? Yes. There's a 100 and there's a 2. We know square root of 100 is 10. We do not know what square root of 2 is, so that would be our final answer. If I'm looking inside of 40 to see are there any cube roots, the only one that comes up is 8. So I could say the cube root of 8 and the cube root of 5, right? 8 times 5 is 40. This guy would make a 2, and the cube root part would stay the same. So this would be my answer. You're just looking for what they have in common. 243. Ooh. It's not on my fourth powers list to memorize, right? Okay, so I'm looking for, is there any number maybe in a third that would come out of this? So if I started thinking about my factor trees, I could say 7, 8, 9. All the numbers add up to 9, which means that it might be divisible by 3. Let's check that out. So if I did 3 times 81, I do notice that 81 is on my fourth power list. Okay, it's going to be 3 to the fourth power. So if this gives me 3, then I have 3. Oops, I put a wrong number there, sorry. 3 fourth root of 3. Okay, keep moving across here. D is asking us for cube roots that are trapped inside 500. 500 is not a cube root, so I would try to simplify it. Maybe you try 2 and 250. That's still not going to work for us. Maybe we try 3 doesn't go into it, so what about 4 and 125? Yep, 125 is a cube root. So I would rewrite this. Cube root of 4, cube root of 125. This gives me the whole number 5. And then I keep my cube root of 4. So this is my final answer. All right, when it comes to using variables, remember that x to the 7th really just means you have 7 x's, and we're trying to put them in groups of 3. So I can make 1 group, 2 groups, and 1 has to be left inside, okay? So I can pull out 2 for the outside. I have to keep 1 inside, okay? Another way you can do this is by a factor of 3. So if I wanted to write it out like this, I could say this is the cube root of x to the 6th times the cube root of just a random remainder 1x. 6 divided by 3 gives me this 2 right here, and then this guy remains on his own. Okay, so there's a couple different ways to look at it. As long as you understand this is your final answer. If you need to pause the screen for a second, go ahead and do that. We're going to do G and H before we go back to F, okay? All right, so looking at G, I'm looking for fifth roots. So fifth root, 64 is not a fifth root. And I'm actually going to keep them all under the same root this time. But we're looking at sets of 5. So if I know that 32 is a set of 5, I could do this as 32 times 2. If I'm looking at the A, and I have 8 of them, I need a set of 5, and I would have a set of 3 left over. For my B's, I have 14. That means I have 10 with a 4 left over, right? Because 10 is divisible by 5. And for C, I only have 1 set of 5. So here's how I would kind of explain that to you. I would say anybody who can act as a fifth root would come out. So that means the 32 fifth root was a 2. I took out 1 set of A's, 2 sets of B's, right? 10 divided by 5, and 1 set of C's. So all of these guys came out. Who's left on the inside would stay with that fifth root. So I had a 2, A to the 3rd, B to the 4th, and that would be the end of my answer. Okay? You don't need the 1 on the A, just so we're clear. All right, let's try one more like that. So for H, I'm looking for cube roots. 81 is not a cube root. So I would need to find a cube root locked within there, and that would be 27. So 27 times 3. If I have 5 x's, that means I have 1 set of 3 and 2 left over. For y's, I have 10, which gives me 3 sets of 3. Whoops, that's 9. And 1 left over. And for z's, I just have 1. So anybody who can be cube rooted goes on the outside. Anybody who cannot stays inside. So my 27 cube rooted turns to 3. I have 1 set of x's and 3 sets of y's. I'm going to keep the cube root though. I have a 3, an x squared, a y, and a z left over. So that is my final answer. Okay? All right, that's all about looking for the nth factor pulled out of the radical. The next thing we're going to talk about is that the index should always be reduced if you can. So if you end up looking at it like a fractional exponent, a rational exponent, if you can simplify that power by thinking about, remember the exponent is your numerator, the radical index is your denominator, then you should always try to simplify that. If we look at f, I could rewrite this as a to the 14th over 4. Now we know 14 over 4 is the same as 7 over 2. So I could rewrite that by thinking about the 2 is my square root and my a would go to the 7th power. These are the exact same thing, just simplified. Okay? Now, if I move from there, I'm saying how many sets of 2 can I make out of 7? Well, I can go into that 3 times, and then I would end up having 1 left over. So a to the 3rd square root of a. What you do not want is saying I had 3 sets from the top, 3 sets of 4 with a remainder of 2. We would not want this part, okay? Because 2 over 4 can obviously simplify to 1/2, which would be a square root. Okay, we want this answer. All right, let's go down to the bottom. Down to the bottom, we are doing the same thing. We are reducing the exponent. So I'm going to rewrite this. X, remember the 4 is the numerator, the 8 is the denominator. 6 is the numerator for y, 8 is the denominator. Now you are trying to simplify it, but you need to make the denominators match because that's the index. Okay, so even though this will simplify to 1/2, this one can't simplify down to a something over 2. So we're going to keep it over 4. So I'm going to say 2 over 4 and 3 over 4. And then I can pull that 4 back out. Remember, if I started with a radical, I need to end with a radical. So I'm going to say the 4th root of x squared y to the 3rd. That's my final answer. Looking at b, we're going to do the same thing. So rewrite it 4 over 8 and 16 over 8. Now this time, this turns into 2 whole, right? So I can simplify the a however I need to. So a to the 1/2, b to the 2nd power. Remember, if it's a whole number, it's going to come out to the outside. So b squared. And then I am going to keep it square root of a. This is my final answer. Oops, I didn't box that one, sorry. All right, we are done with this page. If you need to pause the screen, copy it, go ahead and do so now. We do have one more page to get through. Hang in there. All right, let's talk next about rationalizing and getting rid of any radicand that has a fraction. Remember, radicand is just what's underneath of the square root or underneath the radical. So I can't leave something as the square root of 1/2. Okay, I would not want to do that. All right, first thing you need to know is that if you've copied what's on above, do that now. If you haven't, pause it and do it. Rationalizing means you cannot end up with a radical on the bottom. So you can't have a radical in the denominator. What you're going to do is multiply by 1 to try to get whatever you're taking the radical of. You need the index to match the exponent. Okay? So whatever x is being raised to, I need to have the same radical for that. Okay, here's an example. Let's say I have 1 over the 5th root of x to the 3rd power. I need these numbers to match. So that means I need 2 more x's, x squared, in order to make it 5 and 5. So I'm going to multiply. Let me change colors real quick. I'm going to multiply right here by the 5th root of x squared, because that would make them both end up with a 5. Now, only way to multiply by something and not change the number is to multiply by 1. You'll notice that if you take a number over itself, like 2 over 2, or square root 3 over square root 3, or 5th root x squared over 5th root x squared, all of that is really just 1. So when I multiply this times this, I'm not changing the value. I'm just eliminating the radical on the bottom, okay? So if I say right here, I have 5 sets of x, and I need the 5th root of that, then I just end up with 1x. Now, 1 times this guy obviously is going to simplify. If there was something else with a radical, I would need to put them together. But this would be the exact same answer. I didn't actually change it. It's just written a different way. We call that, it's rationalized. Okay. All right, let's go ahead and do a couple of these worked out. All right, so if I start with A, I'm going to use blue because that's the strategy we're using. Blue is the exact same as saying the square root 2 over square root 3. Remember, I'm trying to get rid of the fraction in the radical. So I need to think about this. Like right now, I have 3 to the 1 power, but I need a set of 2 to pull it out. So I need another 3. So I would say again, square root 3 over square root 3. This is a 1. But now I end up with the square root of 3 squared, which would just give me 3 because they're the same. Okay, the square root and the squared cancel. Now, what's happening on the top is that I'm multiplying 2 numbers under a square root, same index, so I can put them together, square root of 6. So my answer is the square root of 6 over 3. This is rationalized, but it is the same thing as this value. Okay? Let's try B. We're going to do the same thing with cube roots. So I write it out. I already have cube root of 7 separated from cube root of 2. Now, right now I only have 1 2. I need 2 more. So I'm going to cube root 2 squared. And I always write it as the same thing on top. Okay? All right, so now on the bottom, I have the cube root of 2 to the 3rd power, which is just going to come out to 2. On the top, I'm multiplying 7, and remember 2 squared is 4. So now I have the cube root of 28. There's no perfect cubes in there, so I have the cube root of 28 over 2 as my final answer. All right, C, we need to separate them first. So separate gives me 5th root of 3 over 5th root of 4, but instead of writing 5th root of 4, I'm going to write that in the simplest terms. 4 is really 2 squared. So right now I have 2 2's. I need 5. So what that means is I'm going to need 3 more to get there. Always write it under itself. And if you want to go ahead and simplify this up here and say 2 to the 3rd power is 8, you can do that. These two are the exact same thing. Okay. On bottom now, I have the 5th root of 2 to the 5th power. On the top, I have the 5th root of 24. Simplifying, remember if these two numbers are the same, they cancel. So I have the 5th root of 24 over the whole number 2. This is my answer. One more of these guys, okay? So on this one, we're separating them, 4th root of 3. Remember, we're going to simplify that 4 down to a 2. So I have 4th root of 2 squared. I need 4 and I only have 2, which means I need 2 more of them. So 2 squared more. If you want to write 2 squared, that's fine. If you want to keep it as the 4, that's fine too. When we simplify, now I have 4th root of 2 to the 4th power. These are going to cancel. And on top, I have the 4th root of 12. The 4's cancel out, leaving you just a 2 on bottom, and I have 4th root of 12 on top. This is my final answer. If you need to pause the screen, copy anything you missed on that top row, we're going to move to the bottom. All right, moving to the bottom. Remember that a negative exponent moves you down a level. So if this is like a over 1, then what we are basically doing is we are moving it down to the bottom. So if I say I have 1 over a to the 3/8, you could do this with radicals if you wanted to, or you can just understand that you can't have a fractional exponent in the denominator. So the way I look at it is I say, all right, I have 3/8. I need 8/8. Okay? So that means I need 5 more. Because when I get over here, I want to have 8/8. Well, whatever I multiplied, I have to put the same thing on top so that it's equivalent to 1, right? So if I multiply 1 times a to the 5/8, I get a to the 5/8, but 8/8 is just 1. So I would say a to the 5/8 over a. Now, if you did this with radicals, it would be fine. However, you cannot leave an answer like this. So let's say I had done it with radicals and I had gotten this answer. If you start with fractional exponents, you have to end with fractional exponents. You cannot end with a radical. Okay, so one more time, whatever you start with, you have to end with. This would be my final answer I'm expecting. Let's look at F. All right, F looks like he's got a lot going on. He starts with fractional exponents, so he needs to end with fractional exponents. I'm going to stay with exponents, okay? I have 3 out of 4 x's. That means I need 1 more fourth. I'm trying to get 4 fourths. That way I have 1 whole x. That's my goal here. Whatever I multiply on the bottom, I have to do the same on the top to keep it equal. 1 times x to the 1/4 is x to the 1/4. And that is already simplified. So this is my final answer. Does not matter if you use fractions or radicals, you just have to know what you're ending with. Okay, if you need to pause for E and F, go ahead and do that now. We have the bottom section to get through. I know there's still quite a few problems. Just hang in there. If you need to take a break now, go ahead. Otherwise, we're moving on. All right, so down here at the bottom, here is your goal. You are going to simplify each radical first before you put them together, okay? Because if they're not simplified, you do not know if they are like terms, and we can only add and subtract things if they are like terms, okay? All right, so let's start with A. Starting with A, I am looking to simplify, highlight yellow real quick, I am looking to simplify this guy and this guy to see if they're like terms. They both have a 3 for their index, but we don't know if they're the same. So I'm going to put out my 12. Just like we did before, I'm saying I have 2 in there. Can't take a perfect cube out of that, but I do have a set of 3 z's and 2 left over. So this guy can come out. That would make 12z. Ooh, that doesn't look like a z, sorry. And then cube root of 2z squared, okay? So we're trying to get cube root of 2z squared on the other side. Well, that kind of helps me a little bit because that means if I know I need to end up with a 2z squared in here, does 2 go into 54? Yeah, 27 times. And is 27 a perfect cube? Heck yeah, it is. I can pull that out. So now I get 3z cube root of 2z squared, okay? Now that these are the same like terms, that means I can put them together, just like 12zx minus 3zx, okay? I can put them together. And all I'm really worried about is 12z minus 3z makes 9z. This is my final answer. Okay. All right, let's try another one like that. 4b, we have a lot of chaos going on in here. We've got to simplify. I noticed right off the bat that square root 2 is about as simplified as it's going to get. So my goal would be to try to make square root 2's out of this problem. That way I can put them together. Okay, let's go through one at a time. First of all, on top, I need to break apart the square root. So square root of 8 over square root of 9 plus 5 root 2 over 2 minus, and I'm thinking right now, is there anything I can do with square root of 2 or square root of 32? I can put him over 1. That way at least he's a fraction like everybody else. Okay. All right, next row, we're trying to simplify. I know that there's a square root inside of 8. There's a square root of 4, right? So I can say 2 square root 2. And I know the square root of 9 is the whole number 3. I can't do anything with 5 root 2 over 2. It's already rationalized. It's set to go. And I know that I can square root a number inside 32, right? Because that's 16 and 2. Square root of 16, oops, that's a minus, sorry. Square root of 16 is 4, so I have 4 square root 2 over 1. Now, the tricky part with this problem is that unless all of these fractions have the same denominator, then I can't combine them, even though they do all have the same like term for square root 2. So we're going to multiply. Lowest common denominator they can all have in common is a 6. Okay, so let me change colors real quick. All right, to change this to a 6, I have to multiply everything by 2. So I'm going to have 4 square root 2. To turn this guy into a 6, I need to multiply by 3. So I have 15 square root 2. And to multiply this guy into a 6, I need to multiply by 6. So 24 square root 2. Notice I'm not changing the square root 2's. I'm only changing the numbers on the outside. I do want to keep the plus and the minus so I know what I'm working with. Okay. All right. 4 plus 15 is 19. 19 minus 24 is going to give me a negative 5. That square root 2 stays there the whole time. He is not changing. And the denominator is going to stay a 6. This is my final answer. Okay. All right, letter C. Letter C, remember I told you we can distribute exponents, but not if there's a plus or a minus. So because there's a plus or minus, that means we literally want to multiply this by itself. So I'm going to write this whole thing out again. 2a to the 1/3 minus 3a to the 1/2. Okay, we are going to treat this with FOIL. So if I think about multiplying, let me go this way in colors. These by itself, so that ends up with 4. Remember when we are multiplying, that means we add exponents. So that's 2/3. If I multiply to the next one, 2 and negative 3 makes negative 6. But if I add up a 1/3 plus a 1/2, that is not as easy as you think. Remember, that means that we would have to change the denominators to be 6's. This guy would have to multiply by 2. This guy would have to multiply by 3. So we actually are going to say 6a to the 5/6. Okay. All right, let's look at the next one. 3a with a 1/2, he's negative, multiplied by 2, a to the 1/3. That's the exact same thing we just did. So negative 6a to the 5/6. And last one, negative 3 times negative 3 gives us positive 9. 1/2 plus 1/2 gives us 1 whole. So we just have negative 9a with 1 as his exponent. Okay. Remember, you cannot combine like terms, or you cannot combine unless they are like terms. So right here, these are both a to the 5/6, which means they are fine to combine. But I'm going to end up with 4a to the 2/3. Negative 6 is negative 12. Exponents do not change. You are just combining. Plus 9a. This is a final answer. Even though it looks like you should be able to do more with the a's, that's a final answer. If you need to pause the screen, copy down ABC, you may do that now. We're going on to the next guy, or next row. All right. We have a number or a term on the outside multiplied by 2 terms on the inside. This is the same thing like saying 2 times x plus 3. You are just multiplying. Okay. Now, when we multiply, the rule is that we add our exponents. They do not have common denominators. So here's what I would do to start. I would get them all in common denominators to start with. 2 and 5 have a common denominator of 10. So I would erase and make that a 5 out of 10. 2/5 would be 4 out of 10. 1/5 would be 2 out of 10. If you rewrite them all from the start, it makes your life a little easier, okay? So now if I multiply and I add the exponents, 5/10 plus 4/10 makes 9/10. And then 5 times negative x is negative 5x, but we have 5/10 plus 2/10 gives us 7/10. Even though they both have a tenth, 9 and 7 are different. This is a final answer. All right, moving on to E. This is only one term times one term. So when we solve, or when we roll with these, remember, front numbers, whole numbers multiply with front numbers, radicals multiply with radicals as long as their index is the same, which it is. They're both square roots. Okay, so 2 multiplied by a -5 is a -10. Square root of 3 multiplied by a square root of 20. I'm curious if that simplifies. Remember, we're supposed to check it, see if they simplify first. So I'm going to think, does square root of 20 have any perfect squares inside of it? Well, yeah, it has a square root of 4. So let's go ahead and simplify that first. Okay, so if I have 4 and 5, square root of 4 is 2, right? So I'm going to go ahead and pull that on the outside first. That way it's simplified as much as possible, and then we can say the 2 and -10 make -20. The 3 and the 5 make square root 15, and that gives us an easier final answer. Okay. All right, we're going to do the same thing on F. We are not adding and subtracting, so it is okay that they are not like terms. Okay. All right, multiplying these together. Is there anything I can take out a perfect cube here or here? No. So we're going to put them together. 6 and 2 makes my 12. Cube root of 5 and 5 makes 25. A and a squared makes a to the third power. But now that I have a set of a to the third, I'm going to pull that out. So we have 12a, cube root of 25. This is my final answer. All right, let's look at G. All right, looking at G, I have different radicals, and this is where it's going to get a little spicy. I have different radicals, so it's probably easier to think about this with common denominators if we switch to fractions. I'm going to rewrite this as 3 to the 1/3 times 3 to the 1/4, and then I'm going to rewrite this with a common denominator. 3 and 4 have a 12 in common, so let me change colors real quick. To get here, I need to multiply by 3. To get here, I need to multiply by 4. Now I can add them together. 4/12 plus 3/12 gives me 7/12. I cannot simplify that. 7 doesn't simplify with 12. I also don't need to do a 12th root of 3, but I do need to switch it back to a radical, because if I started with a radical, I need to end with a radical. So we're going to say 12th root of 3 to the 7th power. Okay, whatever you start with, format has to match at the end. All right, if you need to pause the screen, go ahead and do D, E, F, G. We have one last row to get through. We're almost there. All right. On this problem, you start with fractional exponents and radicals. So I do not care which one you end with, okay? I think it might be easier to do common denominators if you use all fractions. So here's what I'm going to do. I'm going to rewrite this as x to the 1/6 over x to the 1/5. Remember, I'm trying to get to 5/5. So I need 4/5 more on top and bottom. That way I can get to x to the 5/5. Okay? Now, up here, we do not have common denominators. 6 and 5 are going to need common denominators of 30 in order to add together. So for this one, I'm multiplying by 5. For this one, I'm multiplying by 6. So if I add them together, I get 29 out of 30. Okay, keep the x though. All right, this is almost simplified. Just make sure when you rewrite it that your 5 over 5 cancels and turns to 1, and you end up with just a regular x. I would take this answer, or I would take the 30th root of x to the 29th over x. Either of those are equally okay. All right, moving into I. We do want to simplify first before we put them together. So I'm thinking, are there any cube roots inside of 54? If I divide by a 2, I get 27. So cube root of 2 times 27, that 27 can come out, leaving us 3 cube root of 2. Let's see if we can do the same thing over here with a 4. I know 32 is the 5th root of 2, but is there any 4th root? Yes, we could do the same thing. Take out a 2. That gives us 16, and the 16 can come out as a 4th root. So 2 4th root of 2. We're multiplying, not adding or subtracting, so we don't need like terms. Multiplying these together might be easier if you were to use fractions. So let's say 3, and then 2 to the 1/3 times 2, and then 2 to the 1/4. I am going to convert these into 12ths. Okay, so if you've been paying attention, you know to become a 12th, I need to multiply by 4. To become a 12th over here, I need to multiply by 3. Putting them together, and I'm going to circle back up here. The 3 and the 2 come together to make a 6. The 2 will end up being to the 7/12ths. Now, because we started with a radical, we do need to end as a radical. So 6 12th root of 2 to the 7th power. Okay, you could type in what 2 to the 7th power is, but you do not need to. This is as far as I need you to go. All right, deep breath. We are almost there. Last problem, my friends. All right, for J, we can definitely square root a number inside of 18 because this is 2 and 9. We can definitely cube root a number inside of 16 because this is 2 and 8. So the 8 can come out and the 9 can come out. I'm going to change that into 6 square root 2 multiplied by an 8 cube root of 2. So remember over here, I pulled out a 2. 2 and 4 made 8. In here, I pulled out a 3. 3 and 2 made 6. That's where that's coming from. Okay. I'm going to switch to fractions to make sure that I can get common denominators. So I'm going to go 2 to the 1/2 times 8 and 2 to the 1/3. Common denominator is going to be a 6. So 2 to the 3/6 and 2 to the 2/6. Circle back up here. We are adding those fractions because we're multiplying. 6 and 8 makes 48 when you multiply them together. 2 to the 5/6. And because we started with a radical, we do need to end with a radical. So 48 6th power of 2 to the 5th. And if you wanted to turn 2 to the 5th into 32, that would be absolutely fine, but you do not need to. All right, I'm zooming out. If you missed anything on this page, go ahead and copy it now. Otherwise, we are finally done with the notes for 7.4. Thanks for hanging in there.